Metabolism can be really complicated, but it actually is really logical. And by focusing on the logical principles of metabolism, things like the chemical logic of pathways and the thermodynamic logic, as well as the logic of how it's regulated, can help us understand metabolism as a whole and apply concepts to new scenarios. For example, we saw that the electron transport chain is going to allow us to kind of cache in NADH and FADH2 that we generate from oxidation reactions that can occur through a variety of different processes inside of our cells and the cells of basically every organism. Pretty cool, right? Well, one of the main pathways for catabolism is a pathway called glycolysis. And glycolysis is going to involve the breakdown of glucose to give us pyruvate. All reactions are at least theoretically reversible, but some reactions are what we call metabolically irreversible, meaning that they have such a large negative delta G, they are so favorable in one direction that it's practically impossible to go in the reverse direction. Remember, we can make things change direction by changing the concentrations, because thinking back to our thermodynamics, we know that the concentrations of the products and of the reactants are going to help dictate whether or not the reaction is thermodynamically favorable. One thing that you have to take into account when determining if something is thermodynamically favorable is a standard free energy change. So that's kind of like at equilibrium, if we have these conditions where we have 1 molar of each component and we mix them together and we let them reach equilibrium, will we have more products or will we have more reactants? So we say if we'd have more products at equilibrium, that is going to be a negative delta G naught. And if we had more reactants, then that would be a positive delta G naught. And so if it's negative, then your reaction is what we call spontaneous, or I like to think of it as thermodynamically favorable in the forward direction. And if it's positive, it would be thermodynamically favorable in the reverse direction, or quote unquote non-spontaneous. I really hate the term spontaneous because it implies that it's going to happen kind of instantaneously, but that is often not the case because you often have a large activation barrier. And in fact, it's often going to be the steps, the large changes in delta G, that are going to be the steps that we are going to want to tightly regulate, steps that can kind of serve as go, no go points of your pathway. But one of the big problems too about that delta G naught is that it is not what is happening inside of your cells. And so the concentrations are going to impact the actual delta G, the change in energy between your reactants and your products under the current conditions. If the current conditions are far from equilibrium, then there's going to be a drive to go towards equilibrium to get back to that equilibrium. And as long as we keep the concentrations so that we're not at equilibrium, we're going to have a drive to go forward in the reaction or backwards in the reaction, depending on your perspective. We're going to have a drive to go back towards the equilibrium, and we can therefore manipulate concentrations of things in order to kind of control the directionality of pathways. However, this can only take us so far. We have to take into account that delta G naught prime as well. And if our delta G naught prime is too big, we're not going to be able to overcome it just by messing with our Q, just by messing with our ratio of products to reactants, because we also have to take into account the delta G naught. So our Q is going to get us our products over reactants. It's going to contribute to this part, but our delta G naught is also going to contribute. So if we have a large delta G naught, it's going to make it really hard to reverse a pathway. This is going to come into play when we think about how we could actually go and reverse pathways. If a pathway is thermodynamically favorable in one direction, and we want to make it more thermodynamically favorable in that direction, well, then we're at the same time going to make it thermodynamically unfavorable in the opposite direction. And so we'll see that, well, glycolysis, the breakdown of glucose, if we want to go the other way, if we want to make glucose from non-sugar sources, well, then we're going to need to take a couple bypasses. So there's a process called gluconeogenesis, which is the making of glucose from non-sugar sources. This is going to require a couple of different enzymes than we have in glycolysis. So glycolysis and gluconeogenesis are not just complete opposites of one another. They have the same endpoints, but they go a couple different routes. So they use 7 of the same enzymes However, in gluconeogenesis, we're also going to have this one, this one, this one, and this one. And so we'll see how this is going to come into play when we talk about gluconeogenesis, but let's start by talking about glycolysis. Glycolysis, the breakdown of glucose to give you pyruvate. Later, we'll talk about how you can convert that pyruvate to acetyl-CoA through oxidative decarboxylation. You can see that's going to be oxidative. We're using NAD+, and decarboxylation because, well, we're losing CO2. Along the way, we're going to be generating our NADH, and that NADH can then later be passed on through the electron transport chain to produce ATP. And we're also going to produce some ATP directly in glycolysis. So glycolysis is one of the main pathways of catabolism. It's not the only pathway, and it's going to interconnect with a lot of other pathways. And so we'll talk a little about how we can kind of say, okay, well, do we want to take this glucose to glycolysis? Do we want to take this glucose and hook it up to glycogen? How are we going to control these things? And so that's going to be the focus of later lectures. Today, let's focus on the chemical logic of glycolysis and gluconeogenesis. We talk about how we go through all these catabolic pathways in order to generate ATP by taking the energy from the electrons and using that to make ATP. And we have to use the energy from all these pass-offs in order to produce ATP because that's going to be highly energetically costly. And so if we were to just take ADP and inorganic phosphate or PI, so it's like a free-floating phosphate, and try to join them together, that would cost us 61 kilojoules per mole under standard conditions. That's a lot. That's a lot. However, the conversion of glucose to pyruvate is going to be exergonic, so it's going to give us energy. It's going to give us 146 kilojoules per mole under standard conditions. And remember that we can sum together the standard free energy changes. If we do this, minus 146 plus 61, that's going to give us negative 85 kilojoules per mole as the overall sum of the process of the overall. So we can couple unfavorable things to favorable things, and that's going to allow us to make glycolysis favorable overall, to make the production of ATP via this pathway thermodynamically favorable, because we need it to be thermodynamically favorable in order for this pathway to work. But not all of the steps are going to actually be very favorable. And so we'll see that, however, by manipulating concentrations, by pulling products to drive the reaction forward, by adding reactants, by doing all these things, we're able to change the G, so the actual free energy change, so that we can make this actual free energy change to be at least neutral, so that if it's neutral, we can go either directions pretty easily. And then these steps that we have these big changes, that's where we're going to see differences between our glycolysis and our gluconeogenesis. Overall, however, we're going to make it so that both gluconeogenesis and glycolysis are thermodynamically favorable. And we're able to do this because they're not just opposites of one another. They do have those differences. So let's dive into the similarities and their differences. We're going to go several times through the glycolysis pathway, and each time we're going to add a little more detail. I'll take you once through the basic reactions. I'll take you again through the reactions, focusing more deeply on the chemical logic. And then I'll take you another time, tying in connections to other pathways and to gluconeogenesis. So, are you ready? Let's dive in. Glycolysis happens through two main phases. We have the energy investment phase, where we're going to kind of have to spend 2 ATP. And then we have the energy payoff phase, where we're going to produce 4 ATP and 2 NADH. On net, therefore, we spent 2, we made 4, so we have 2 ATP on net and 2 NADH on net. Why is it 4 in the bottom when you only see, okay, well, I see 1 here and I see 1 here. How do we get 4? Well, we'll see that the second part of the pathway is actually going to happen twice because we split the glucose, or at this point, the fructose 1,6-bisphosphate, into 2 at the end of the energy investment phase. So let's start by thinking about the chemical structure of glucose. We have 6 carbon. We see that there's already a lot of oxidation that's happened. If we were to compare it to like a lipid, we see that there's a lot more bonds to the oxygen, fewer bonds to hydrogen and things like this. So it's not saturated with hydrogens. However, there's still a lot of oxidation potential that can happen because remember, the maximum oxidation a carbon can have is to be CO2. And so that's to basically be attached to 2 oxygens and no hydrogen. So 2 bonds to each oxygen, and each oxygen is kind of taking the electrons from those bonds. So that would be your fully oxidized. And remember, oxidation is loss of electrons. Those electrons can get transferred to NAD+, and that NAD+ can then be taken to the electron transport chain where you can get ATP produced. And remember that for each NADH you produce, you're able to make like 2.5 ATP. And so you actually make more ATP from that NADH that you generate than you actually do through glycolysis. And so glycolysis is one route to get us some of the energy, but it's really the big payoff we'll see is going to come later from the NADH that we generate mainly through our citric acid cycle, which we can do after we convert that pyruvate to acetyl-CoA. But that's next. Let's go back to our glycolysis story. We got those 6 carbons. Now what we're going to do is we're going to take them through a couple reactions. We're going to split it in half to give us 2 3-carbon compounds. We're going to remain 3-carbon compounds throughout the rest of the pathway. However, we're going to transfer things around. We're going to phosphorylate. We're going to dephosphorylate. And we do all the switching around in order to set up the scene for making the interactions that we want to be favorable. If we look at what's going on, we can see that the glucose is first going to get phosphorylated at the 6th position by an enzyme called hexokinase. A version of hexokinase in your liver, the isoform in your liver, is called glucokinase, and it's going to be regulated separately. And so that's just a note, if you see glucokinase, that's going to be an isoform, an isozyme of your hexokinase, an isozyme that you find in the liver. But going back to this story, either hexokinase or the form called glucokinase is going to phosphorylate glucose to the 6th position to give us glucose 6-phosphate, sometimes abbreviated G6P. Next up, there's going to be an isomerization reaction catalyzed by phosphoglucose isomerase. If you look and kind of compare the before and after, we can see that here we have an aldehyde, so we have our carbonyl at the end. Here we have a ketone, we have our carbonyl in the middle. And what we've done is we've basically freed up an alcohol group at the end that is going to then allow us to phosphorylate that position. And when we phosphorylate the position, well, now we phosphorylated both ends of the compound. We can split this in 2, and we'll still have two parts that are phosphorylated. There's a couple purposes to having this phosphorylation. One is that it's going to kind of trap it in the cell, keep it from diffusing out. Because remember, the lipid bilayer is not going to let through those charged things. And so by cutting this in half and keeping the little intermediates charged, we can keep them from floating out of the cell. Additionally, phosphates are going to offer potential places where we kind of have stored energy that we can then use to power reactions that might not be very favorable. Phosphofructokinase is going to carry out that phosphorylation. That's going to happen at the 1 position of your fructose 6-phosphate that you generated from your isomerization. So you're going to end up with fructose 1,6-bisphosphate or F16BP. And by having the phosphorylation on both ends, we'll be able to split things up and still have 2 kind of equivalent halves, or at least halves that we can convert to be equivalent to one another. So that's what we're going to do. Fructose bisphosphate aldolase, more frequently just abbreviated aldolase, is going to split this molecule in half to give you 2 3-carbon compounds, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate. Glyceraldehyde 3-phosphate is the one that's going to actually carry on in the glycolysis. Dihydroxyacetone phosphate needs to be converted into glyceraldehyde 3-phosphate if it wants to carry on. Thankfully, there's an enzyme called triose phosphatidylisomerase, or TPI, that is going to carry out this interconversion and allow the reaction to all kind of get pulled towards the glyceraldehyde 3-phosphate. So although you start with equal amounts of these 2, because you're pulling the G3P forward, the dihydroxyacetone phosphate is going to be kind of pulled towards it. This triose phosphatidylisomerase reaction is going to be favorable in the production of G3P production, which is going to drive the pathway forward. Next, you're going to add another phosphate group with glyceraldehyde 3-phosphate dehydrogenase. So when we think about phosphorylation, we're often talking about using a kinase. A kinase is typically going to add a phosphoryl group, which is going to be a phosphate with 3 oxygens. In the case of, and that phosphoryl group is going to be coming from ATP. But in the case of this reaction, we're actually adding a phosphate group, which is a phosphorus surrounded by 4 oxygens. In this case, we're not just kind of like we're actually adding an oxygen. And so this is going to be an oxidation reaction. And in fact, the energy from this oxidation reaction from the passing of electrons from glyceraldehyde 3-phosphate to NAD+, that's going to be enough energy to power the addition of this phosphate group without needing to like spend ATP. And so the energy for this is coming from the oxidation reaction of the molecule. And we're also going to be generating an NADH. So this is an example of an oxidative phosphorylation. Often when we talk about oxidative phosphorylation, we're discussing it in the sense of the electron transport chain and oxidative phosphorylation, where the electron transport chain, we have oxidation through those reactions that's going to be powering the production of ATP. This, however, is another form of oxidative phosphorylation, and this is a more kind of like direct oxidative phosphorylation. But remember that typically when you hear the term oxidative phosphorylation, that's going to be referring to the production of ATP following the electron transport chain and using the power of the gradient in order to power the production of ATP. Now, however, we've made an NADH, which remember we'll be able to cash in for 2.5 ATP through the electron transfer chain and that oxidative phosphorylation process that's happening in your mitochondrial matrix. But for now, we have this NADH that we've generated. And now we have this 1,3-bisphosphoglycerate. So what we did here was now we're back to having a molecule with a phosphate on each end. Now that we've kind of added the phosphates, we added an inorganic phosphate. So remember, this phosphate was not coming from ATP. It was just a free-floating phosphate. Now we're going to actually use it to make ATP. We're going to pass it off from this 1,3-bisphosphoglycerate onto ADP to give us 3-phosphoglycerates. We're going to do this using a molecule called phosphoglycerate kinase. Don't get confused by the names. So remember that when we talk about a kinase, it's normally taking ATP and putting a phosphate group on something. However, we're kind of thinking about things in the opposite direction here. So remember, every reaction is at least theoretically reversible. And this reaction actually is reversible. So phosphoglycerate kinase is able to kind of take that phosphate group off of the molecule and stick it onto ADP to give you ATP, as opposed to taking the phosphate group off of ATP and sticking it onto the molecule, which is what it would do in the opposite direction. And so that's what you're going to see in gluconeogenesis, is that ATP will be transferred onto this 3-phosphoglycerate in order to give you the 1,3-bisphosphoglycerate. However, if you're thinking about it in the glycolysis direction, we're going to be making ATP from this phosphate group. You might be confused and wondering, what's the difference between a phosphatase and a kinase? Because typically we talk about a phosphatase as something that removes a phosphate group and a kinase as something that adds a phosphate group. But now we're talking about a kinase as something that can remove a phosphate group as well. The difference is that a phosphatase is going to use water to kind of break off a phosphate group. And we'll see an example of a phosphatase later when we talk about gluconeogenesis. We'll actually see a couple of examples. In those cases, we're using water to break off a phosphate group, as opposed to transferring, or at least, I guess, a phosphoryl group, as opposed to transferring that phosphoryl group from one molecule to another. So in this case, we're transferring it from one molecule to another, rather than just kind of breaking it off with water in a hydrolysis reaction. So keep that in mind, and we'll get back to it later in our story. And the reason why this one's kind of more reversible, whereas normally if you have a kinase, it's not, is because you're transferring that phosphoryl group from kind of similar location to similar location, energetically wise, and that's going to make it so you can kind of just go back and forth with this, as opposed to a kinase, where you're kind of making a more dramatic swap of what that phosphoryl group's getting attached to. And in those cases, you are going to have to then use a different pathway in order to reverse it. You're typically having to use, say, phosphatase and hydrolyze the phosphoryl group off that way. At this point, we have 3-phosphoglycerate, and we want to convert it to 2-phosphoglycerates. If we want to do this, basically we're just shifting the position of this phosphoryl group. And when we do this, well, that's just an isomerization reaction. Remember that one of the common names for an isomerase, or a special type of isomerase at least, is a mutase. And so phosphoglycerate mutase is going to take this 3-phosphoglycerate and it's going to convert it into 2-phosphoglycerate. By doing this, you set up the scene for this enolase reaction. In this enolase reaction, you are going to then basically lose water. So this is going to be an elimination reaction. You're going to form a double bond here. You're going to introduce something called an enol. So you have a carbon-carbon double bond, an alkene, next to the kind of like an alcohol. If you were to lose this, this is going to trap it in this unfavorable enol form. Then if we split off that phosphate group, that's going to be favorable. We can take that phosphate group, put it onto ADP to give us ATP. And this is then going to allow us to make ATP and leave us with this pyruvate molecule that then we can take further through our catabolism if we want. Sometimes you'll see this term, substrate level phosphorylation, for reactions like this where we're transferring a phosphate group from a small molecule onto ADP to give us ATP, as opposed to sticking like a phosphate group onto ADP to give us ATP. Let's start at the very beginning. That's a very good place to start, don't you agree? I hope so. Anyways, we're going to start there anyway. So glucose, we're going to take glucose, and now we want to take this glucose that entered the cell, and we want to say, okay, glucose, stay in the cell. And so glucose is going to come into the cell through various transporters, including transporters that are kind of just allowing for diffusion. And if we just allowed them to diffuse in and out of the cell, and then we didn't trap them inside of the cell, the concentration inside of the cell would equal the concentration out of the side of the cell. And we could have the glucose actually floating back out of the cell. However, if we drop the glucose, well, now we've changed its form, so we've messed with that equilibrium, so we're able to keep bringing glucose in, and we're able to prevent the glucose from kind of floating out. Because your cells don't have transporters for that glucose 6-phosphate, just for the glucose, and so now you can trap the glucose in the cell if you phosphorylate it. And so that's what you're going to do. You're going to phosphorylate it using that hexokinase. Remember, hexokinase, the form in your liver, is called glucokinase. You're going to phosphorylate this 6th position, and that's going to give you this molecule of glucose 6-phosphate. Now, this reaction, if we look at the delta G, so here it just says G, but it's a free energy chain, so it's actually in delta G, don't get confused. And here it's in kilojoules per mole. Sometimes you'll see things in kcal per mole. But remember that you can easily interconvert between the two of them. In this step, we are taking the phosphate group from ATP, and this is going to leave us with ADP. The free energy change from this. Remember how we talked about the hydrolysis of ATP? How the breaking of that bond was not going to be energetically favorable, how it's always going to be endergonic to break a bond. It's always going to require energy to break a bond. However, if we consider kind of what you get out of it, if we consider the reactions that happen afterwards, if we consider the resonance stabilization of the phosphate group, if we consider the resonance, if we consider the charge repulsion, all of these things that come from the hydrolysis of ATP that are going to make it thermodynamically favorable are going to make it so that we can then power the hydrolysis of this ATP in this reaction in order to add this phosphate group onto the molecule. This inherently is going to have a negative delta G naught. However, we're going to make it even more negative. And so how can we make it more negative? Remember that even inherently favorable reactions are going to depend on concentrations. And so if we can keep a high ATP-ADP ratio, we're able to make this even more thermodynamically favorable. And this step is therefore going to serve as a really important energy investment phase where you're kind of saying, okay, you're committed to staying inside of the cell. We'll talk later about how once it's kind of trapped inside the cell, however, it can have multiple fates. It can go and get linked up to form glycogen. It can go and it can get taken down the pentose phosphate pathway, or it can go down glycolysis. And so we're going to focus on glycolysis now, but know that kind of when we talk about a committed step in glycolysis, we're actually going to be talking about this phosphofructokinase, because this is where we're kind of going to be committing to glycolysis. When we're at this glucose 6-phosphate phase, we can still kind of go a bunch of different directions. For now, however, we're going to focus on going down this direction of glycolysis. We can easily interconvert between glucose 6-phosphate and fructose 6-phosphate using phosphoglucose isomerase, which we'll look at in a minute. And therefore, because this step is easily reversible, this step isn't going to really commit you to glycolysis as well. However, this fructose 6-phosphate phase, this is actually is. And so this is what we're see. We're going to have kind of the biggest regulation is going to be at this PFK1 step. So we consider this the committed step of phosphor. So we can consider this the kind of committed step of glycolysis as opposed to this phosphoglucose isomerase step. In this phosphoglucose isomerase step, basically here we're just shifting things around. We're going to free up the alcohol, the hydroxyl group at the end. That's going to allow us to have a position where we can phosphorylate. So phosphoglucose isomerase, sometimes you'll see this called like phosphohexose isomerase. This is going to shift things around. It's going to free up that position, and then we're going to be able to phosphorylate it. You'll see that this reaction has a pretty neutral G or delta G, and that's going to make it so that it's easy to go back and forth depending on the relative concentrations of things. This is going to allow for flexibility in the usage of glucose, where if you have a lot of fructose 6-phosphate buildup, well, now what's going to happen is that's going to promote the back direction to make more glucose 6-phosphate. And so now you might say, okay, well, we're kind of slowing down on the breakdown. We're kind of building up a backlog. Why don't you go and you make some glycogen or something like that? So we're able to control the directionality of this by controlling the concentrations. However, now we get to this step where we're actually going to invest another ATP by phosphofructokinase. This step is kind of going to be our committed step of glycolysis, because once we go here, there's not an easy path backwards into one of those other pathways like glycogen metabolism or your pentose phosphate pathway. So this PFK1 step is going to be a really important step of regulation. And in the next lesson, we'll look at how in detail at this regulation. For now, let's go back to looking at the chemical logic of it, however. This is just going to be a simple phosphorylation reaction where we're going to take a phosphoryl group, so remember that's a phosphate with 3 oxygens, from a ATP and stick it onto our molecule, leaving us with ADP. And in this case, we end up with this molecule, F16BP, or fructose 1,6-bisphosphate. Note here, we'll come back to this is going to be different in gluconeogenesis. At this point, we phosphorylated both ends of this molecule. We've kind of committed it to glycolysis, and we're ready to split things up. One of the benefits of kind of splitting things up is that now you have pieces that you can take in different pathways, so you don't have to commit all of the glucose, say, to glycolysis, and you can have pieces that you can then go and use. So see, for example, that one of the products of this, dihydroxyacetone phosphate, or DHAP, can actually be used to make glycerol, which can be used to make your triacylglyceride, so like your fats to store. And so by having these little pieces, you're able to kind of have enzymes put together these pieces kind of like Lego blocks that you can build lots of different molecules from these smaller intermediates, as opposed to having to have enzymes that can, with big molecules and much more different molecules than kind of smaller parts that you can put together in different ways. So to get these small parts, however, we need to break up these bigger molecules. Fructose bisphosphate aldolase, more commonly just referred to as aldolase, is going to be able to break this F16BP, this fructose 1,6-bisphosphate, into these 2 3-carbon compounds. One of the compounds I just mentioned was dihydroxyacetone phosphate, or DHAP, and the other is going to be glyceraldehyde 3-phosphate, or G3P. It's this G3P that's actually going to continue on in the pathway, but we'll see next that DHAP can actually be converted into it. If we can compare the chemical structures of these, so the word aldehyde, remember that aldehyde is going to be a carbonyl at the end. So this is going to be an aldehyde group at our glyceraldehyde 3-phosphate. We have our phosphate position on the phosphate at the 3 position, and we have our aldehyde at this first position. And remember that the structure of a glycerol was going to be 3 carbons with OH groups. And so we can see here that here we've got the phosphate instead of an OH group here, and we have an aldehyde instead of just an OH group here. One of the interesting things, too, is that if you look at our delta G for this reaction, you'll see it's -6 to 0. So it's actually going to be pretty neutral in order to do this, and therefore we can easily go back and forth. However, if you look at the delta G naught, you'll see that it's 23.8, which would indicate that it was going to be very thermodynamically unfavorable to go forward in this reaction. How can we therefore make it go backwards and forward so easily? And that gets back to our idea of the reaction quotient. So having to take into account the concentration of your products and reactants in order to know what the actual free energy change is going to be. Remember, good old Le Chatelier's is going to be true no matter how kind of inherently thermodynamically favorable your reaction is. It's just that if your reaction is really thermodynamically favorable or unfavorable, you're going to have a more skew in your product reaction ratio in order to actually change the directions, but you could change the directions. And so by pulling this by pulling the G3P forward in the reaction. You're driving this reaction forward. You're taking away the products. You're taking away the products. You're going to make this reaction like driven forward. You're taking away those products. This is going to get lower. You're going to end up so that you're going to have a Q that is going to be less than your KEQ. So remember, KEQ is saying at equilibrium, what would the ratio of products to reactants be? And your Q is saying right now, what is the ratio of products to reactants? If we have less of our products, we're going to have this be lower. We're going to therefore have our Q less than KEQ. This is going to be favorable. So in this way, we're able to make it favorable in the forward direction. We can also remove the DHAP. We can remove it by interconverting it to G3P, or we can actually go take it out into other pathways, such as for making glycerol. We can interconvert glycerol to DHAP if we want to add more into the pathway to make glucose from glycerol that we get, say, from breaking down our fats. So lots of interconversion between these pathways. So you can get that DHAP either from this aldolase reaction or from your glycerol. But one way or another, you're going to then have to convert it to the G3P in order to continue on with your glycolysis. This can take place through this enzyme triose phosphatidylipomerase. What triose phosphatidylipomerase is going to do is it's going to kind of switch the place of things. So isomerase, remember this isomerase is just changing the position of things within a molecule. And the triose phosphatidylipomerase, so triose, because it's a ose is a sugar, it's got 3 carbons, tree, and it's got a phosphate, and it's moving the position of things. So it's a triose phosphatidylipomerase. In this condition, in this case, it's going to be converting dihydroxyacetone phosphate, or DHAP, to glyceraldehyde 3-phosphate, or G3P. And you can just see that it's basically changing the place of this OH group versus the carbonyl group. So we go from having a ketone to having an aldehyde, with more specifically a glyceraldehyde 3-phosphate. This is a pretty energetically neutral reaction, so we can easily interconvert these. Once we interconvert these, we can't really tell what came from what. The easiest way I find to think about it is to kind of just think of the positions that have the phosphate groups as being kind of identical once you interconvert things. And so the conditions of the phosphate groups aren't going to change. So the 1 position is going to be equivalent to the 6 position. The 2 position is going to be equivalent to the 5 position. And the 3 position is going to be equivalent to the 4 position. And you can't kind of tell those two apart once you interconvert them to being the same thing. This can come into play if you're trying to do some sort of metabolic tracking. And so you have a radioactive version of some of the carbons, and then you go and you trace it. You wouldn't be able to tell apart things after that step. Going back to our story, we've converted all of the DHAP to the G3P. And now we want to take that G3P, so remember that's a glyceraldehyde 3-phosphate, and we want to actually make it 1,3-bisphosphoglycerate. So we're going to stick another phosphate group onto it. We're going to stick this phosphate group onto it, not a phosphoryl group, not a phosphoryl group. So we're actually sticking a phosphate group, so a phosphorus with 4 oxygens. When we're adding this extra oxygen, we are going to be doing an oxidation. If we're doing an oxidation reaction, remember we're often going to be using NAD+. We are going to be reducing NAD+ by transferring electrons from a molecule onto it. We're going to transfer electrons from our glyceraldehyde 3-phosphate onto NAD+ to give us NADH and leave us with 1,3-bisphosphoglycerate. And where's the energy coming from? It's coming from those passings of electrons. Remember that passing electrons from something with a lower reduction potential to something with a higher reduction potential is energetically favorable, so it releases energy. NAD+ is going to have a higher reduction potential than our glyceraldehyde 3-phosphate, and therefore it's going to be energetically favorable to pass electrons to it. And the energy from that can be used to phosphorylate this glyceraldehyde 3-phosphate. Additionally, because we keep those NAD+ ratios really high compared to our NADH, that's going to make it so that this is even more thermodynamically favorable. However, if we were to get to conditions where our NADH was high, then this reaction would no longer be able to proceed. Glycolysis would no longer be able to proceed. Things would have to go the other direction or stop. But we'll get back to that when we talk about anaerobic respiration. For now, let's continue on our story with 1,3-bisphosphoglycerate. So we added a phosphate group to both ends, and now we're going to take off the phosphate group and transfer it onto ADP to give us ATP. We are taking this 1,3-bisphosphoglycerate, and we're going to be left with 3-phosphoglycerate. So we're taking off that phosphate that we just added to the top. And so we took that phosphate from the inorganic phosphate, added it to G3P. Now we're taking it off of G3P and putting it onto ADP. Why? Why? The reason why is because we didn't have enough energy initially in order to stick that phosphate group onto ADP directly. However, by first sticking it onto the G3P to give us 1,3-BPG, now we do have enough energy in this acyl phosphate bond in order to power this. So an acyl group, this is just where you have a carbonyl next to a carbon and next to something. And so this is kind of like your generic acyl group, this carbonyl right here, and it's next to this phosphate group. So we can call this an acyl phosphate group. This is going to be one of those kind of like quote unquote high energy bonds. And so remember, it's not that the bond itself is going to be like, generate energy by breaking it, because breaking of a bond is always going to be entered on it. It's always going to take energy. However, what you get in return is going to be more favorable. And so we can think of it as kind of like storing energy, and the energy you get from this can be used to pass the phosphoryl group. So again, the phosphate group with 3 oxygens in this case, pass the phosphoryl group onto ADP to give us ATP. And that is going to be an example of a substrate level phosphorylation, where we're passing a phosphoryl group off of a small molecule onto ADP to give us ATP, as opposed to passing an inorganic phosphate onto ADP to give us ATP. This pathway is going to allow us to have a fairly neutral delta G. Fairly neutral, so we can go back and forth. We can use the same enzyme in both our glycolysis and our gluconeogenesis. Let's compare this 3-phosphoglycerate to the glyceraldehyde 3-phosphate. Because we said, okay, we put the phosphate on the first position, and now we took a phosphoryl group off of the first position. So we are not left with the same molecule we had before. Now we're in an oxidized position. We are oxidized, we have this oxygen here, as opposed to here we just had this aldehyde at the end. Now we have a carboxylate group. And so we have used the energy that we transferred onto this NAD plus to give us NADH, and we've used energy to kind of produce ATP in this step. So we've used some of the energy that we had here, but there's still lots of places in which we can oxidize and we can generate ATP and we can generate NADH. So let's continue on in our pathway. In order to continue on, we need to shift things around again. And remember, if you want to shift things around, that's going to be isomerization. You're going to want an isomerase. One of the types of isomerase we have is a mutase. In this case, we have phosphoglycerate mutase is going to shift that phosphate group from the 3 position onto the 2 position. Why the heck do you do that? Well, why the heck you do that is because now you're going to set things up for the next step. And so this is kind of like a preparatory step. Not too exciting. You're just kind of shifting things around. You can see it's got a pretty neutral delta G. So you're able to go back and forth fairly easily. And this is going to be your phosphoglycerate mutase step. Don't get fooled, however, because although it looks pretty boring, it's actually really exciting. Because now what you have is you set the scene up for enolase to play its part. Enolase is going to, this one is kind of one of those where you kind of just have to remember the name of it, because it's not very intuitive how the naming works, but it's enolase. And what it's going to do is it's going to kind of like eliminate water. And so it's going to kick out water, make this double bond between these carbons. And you're able to now have something called an enol. Or what will be an enol in a second. So an enol, so we have ene, remember the ending ene, that's going to refer to like an alkene, and we have an alkene, that's a double bond between 2 carbons. So this is an alkene, and then this would be an alcohol once we lose that phosphate group. So if you think about this, we have an enol would be an alkene with alcohol group. And then if we think about a ketone, then that would be a carbonyl surrounded by carbons on both sides without any double bonds, at least between the carbons. So this would be referred to as an enol, and this would be referred to as like a keto. The keto form is going to be much more favorable than the enol form. If you were to just mix these together and you let them reach equilibrium, say, what's going to happen is you find a lot more of the keto form. So these can interconvert. You can think about the electrons from this double bond to the oxygen kind of flowing back down to form a double bond to this carbon, and one of the protons from this carbon kind of shifting over to this oxygen. That can happen, and that's the process called tautomerization, where you kind of interconvert between the enol and the keto forms. However, the keto form is going to be greatly preferred, so if you allow for tautomerization and you were in the enol form, you're going to go to the keto form. That's what would normally happen. However, in the case of our phosphoenolpyruvate, what you have is you've got it kind of trapped in the enol form because instead of just having an enol, you actually have a phosphate group here. And you have to kick out that phosphate group if you want to go and you want to tautomerase to make pyruvate. And so that's what you're going to do is you're going to kick off that phosphate group. You're going to transfer the phosphate group onto ADP, similarly to what we saw before, where we were transferring a phosphate group on to ADP to give us ATP. We're going to be doing similarly here. We're going to be transferring the phosphate group, this time from the 2 position of our phosphoenolpyruvate onto ADP to give us pyruvate. This pyruvate is then going to be able to travel further on in the pathway. And we're able to do this because we're kind of trapping this enol form. Once we release that phosphate group, now we're able to tautomerize into the keto form. The energy from that tautomerization is going to be very, very favorable. It's going to drive this reaction forward. And we'll see that we have a negative delta G, a very negative delta G, a big bang at the end of the pathway. So you can see that if we look here, we have phosphoenolpyruvate. The hydrolysis of that phosphoenolpyruvate is going to be about minus 61.9 kilojoules per mole under standard conditions, or that would be equivalent to 14.8 kilocalories per mole. If we are to think about the hydrolysis of ATP, if we think just about the hydrolysis of ATP to ADP, here it would be minus 30.5 kilojoules per mole, or 7.3 kilocalories per mole. So we have about twice as much energy from the hydrolysis of that phosphoenolpyruvate than we have from the hydrolysis of ATP. And this means that we have more than enough energy to kind of make ATP from the energy that we have in that phosphoenolpyruvate. Similarly, we see that if we look at the 1,3-bisphosphoglycerate, we have more than enough energy in this bond as well to make ATP. Therefore, we're able to use these kind of high energy bonds in order to make the ATP without having to go through the electron transport chain and your oxidative phosphorylation. However, remember that from the electron transport chain and oxidative phosphorylation, you can get a lot more energy. Say, however, you're not able to go through the electron transport chain. For example, in your red blood cells, they don't actually have mitochondria. Mitochondria, remember, is where the electron transport chain happens. If you don't have mitochondria, you can't do the electron transport chain, and therefore you can only kind of get energy from your glycolysis or similar reactions. This can also happen if you kind of don't have enough oxygen or if you are just kind of working too hard and you run out. You can't keep up, like your muscles. In those cases, you want to keep doing glycolysis to get that ATP. However, you can't do the aerobic respiration. You can't do the stuff that actually requires oxygen. You can't do that stuff that's in the mitochondria, all that electron transport chain and that sort of oxidative phosphorylation. You have a problem, however, because remember when I mentioned NADH and how you're making NADH? Well, in that having a high concentration of NAD plus is actually going to drive this forward. If you have a high concentration of NADH, well, now you can't go forward in glycolysis. You could go backwards, but you can't go forwards. And what's worse is that the NADH is actually going to be inhibiting glycolytic enzymes, as well as some enzymes in like your TCA and stuff. Bottom line is you want to keep that NAD plus to NADH ratio high. You want to prevent the buildup of the NADH, which is going to inhibit things and keep you from going forward in glycolysis. Typically, you're going to have that NAD plus regenerated in your electron transport chain. However, in the case that you can't do that, now you have lactate fermentation offer an alternative. You take the NADH that you made, reduce that pyruvate to lactate, using an enzyme called lactate dehydrogenase. Note that lactate and lactic acid, these are just the acid and conjugate base forms of the same molecule. So you can kind of use those terms interconvertibly, and you will see both used interconvertibly. But by this kind of uses up your NADH, so you are losing out on the opportunity to make an ATP from that NADH. However, you are able to generate the NAD plus and keep the pathway going. There's actually a pathway in your liver called the Cori cycle, where basically what's going to happen is your active muscles are going to transport that lactate that they generate to the liver. The liver is going to have it use its lactate dehydrogenase to reverse things. So it's going to take NAD plus, and it's going to take that lactate, and it's going to oxidize the lactate to give you pyruvate, which the liver could use to oxidize further for more energy. Or in the case of the cycle, it can actually use it to make glucose in gluconeogenesis that it can then send back to the muscles. So now let's talk a minute about gluconeogenesis. So remember that gluconeogenesis is kind of similar to reversing glycolysis, and a lot of it is just reversing glycolysis. However, there are three kind of bypasses, and those bypasses are going to take place at those kind of irreversible steps. So those metabolically irreversible steps, those steps with a really high change in delta G. That's going to be our hexokinase step, our phosphofructokinase step, and our pyruvate kinase step. So the steps at which we spent ATP in the beginning, our investment, and our big bang at the end, where we're generating ATP. Those steps are going to require bypasses in gluconeogenesis because those steps are going to have this really negative delta G that is going to be pretty impossible to reverse just by changing the concentrations. Or if we were to change the concentrations, well, now what would happen is that we would be making it so that it would be impossible to do glycolysis. And so most of these steps you'll see have a very neutral G, a neutral delta G, so we can just kind of change the concentrations and go back and forth. However, at these steps where we have these more big energetic changes, we're going to want to regulate them enzymatically. And so we'll get into this in the next lecture. However, let's just look at the chemical steps that take place in these processes. Let's start from the bottom up. So say we have that pyruvate and we want to go take it back up through gluconeogenesis. We're going to need two enzymes to do this. We're going to need pyruvate carboxylase, and we're going to need PEP carboxykinase. So pyruvate carboxylase is going to use ATP in order to carboxylate. So in order to add a CO2 group to your pyruvate to give you oxaloacetate, that's going to be energetically costly. So it's going to take ATP. It'll leave you with oxaloacetate. The second enzyme, PEP carboxykinase, or PEP-CK, is going to use another ATP or GTP, depending on which isoform and stuff you're using. And it's going to then phosphorylate the oxaloacetate to give you that phosphoenolpyruvate. It's going to take back off that CO2 that it just put on, but it put that CO2 on in a strategic position so that it could use it to power the phosphorylation. And that's going to therefore allow for the generation of this phosphoenolpyruvate. Note that in glycolysis, we were generating 1 ATP at the step, whereas for gluconeogenesis, we're actually spending 2 ATP at the step, or ATP equivalents. And so therefore, this is going to be even more costly than just kind of reversing the pathway. However, we are able to make it happen. Somewhat complicating matters is that there are actually a couple of different ways in order we can make it happen. The first step, this pyruvate carboxylase step, that has to be carried out in the mitochondria. That's the only place it is. However, we have both cytosolic and mitochondrial versions of PEP carboxykinase. So that second step we can actually do in the mitochondria or in the cytoplasm. However, we cannot take oxaloacetate out of the mitochondria. Therefore, we either convert to phosphoenolpyruvase inside of the mitochondria and take the phosphoenolpyruvase out, or we do that first step that we take that oxaloacetate and we convert it into malate, take that malate out and convert it back into oxaloacetate to make your phosphoenolpyruvate in your cytoplasm. This is using our favorite enzyme, malate dehydrogenase. In this case, malate dehydrogenase is going to, you'll have a version in your mitochondria and a version in your cytoplasm. And the malate dehydrogenase is able to interconvert the oxaloacetate and the malate to convert the oxaloacetate to malate inside of the mitochondria, and then convert the malate to oxaloacetate outside of the mitochondria. You might wonder why we have these two separate pathways. Let's think about what happened in both of these cases. If you do both steps in your mitochondria, you're not doing any oxidation or reduction inside of your mitochondria, and so you're not kind of taking any equivalents in or out of the mitochondria. However, if we go and we convert to oxaloacetate, so we do that pyruvate carboxylase step inside the mitochondria, remember that step we have to do inside of the mitochondria, but then we convert it to malate inside of our mitochondria, and we take that malate out. To go from oxaloacetate to malate, that's a reduction reaction, so we're using NADH. To reverse it in the cytoplasm, we're going to have to do an oxidation reaction. We're going to have to kind of regenerate that NADH in the cytoplasm. In the process, we've taken the equivalent of an NADH out of the mitochondria, and this is therefore going to kind of allow us to have NADH that we can use later in glycolysis for that step where we needed NADH to go from 1,3-bisphosphoglycerate to glyceraldehyde 3-phosphate. So if we want to do gluconeogenesis and we're starting just from pyruvate, it makes sense to go this route because now we're taking an NADH out into the cytoplasm where we can use it. However, think about if we had the energy coming from lactate. In the case of lactate, remember like in our Cori cycle, what would be happening here was that we would already have to oxidize lactate to go as pyruvate. We'd already be generating the NADH in the cytoplasm. And so we don't need to bring out another NADH in order to kind of just keep the cycle going. We have the NADH already generated in the cytoplasm, so we can do both steps in the mitochondria, take that PEP out, and take it further. And note here that this is also the place, remember, where we can take that glycerol and convert it to dihydroxyacetone phosphate and enter the pathway that way. So glycolysis, where you're breaking down glucose to give you pyruvate. Gluconeogenesis is where you're making glucose from non-carbs. Don't confuse those with glycogenesis, which is the making of glycogen from glucose, or glycogenolysis, which is the breakdown of glycogen into glucose, or technically glucose 1-phosphate. So that'll reverse this kind of bottom step, but we still have these two other steps to overcome. The phosphofructokinase step, which remember, that was our kind of like committed step of glycolysis, because we say that if we go this step, well, now we're kind of committed here, whereas this glucose 6-phosphate, we can go different ways. In this, if we need to therefore regulate this step really tightly so that we only go down this pathway if we want to go to glycolysis. And similarly, if we want to go back, well, now we're going to have to regulate the other direction. And so we're going to need a separate enzyme here. We're going to use this fructose 1,6-bisphosphatase. Phosphatase, we're finally seeing our phosphatase. So remember, a phosphatase is a hydrolase. It's going to use water to cut off a phosphate group in a hydrolysis reaction. So a simple hydrolysis reaction is going to be able to allow us to reverse that. In order to reverse the first kind of step, the hexokinase step, we're going to need another phosphatase. Again, just a simple hydrolysis reaction. In this case, glucose 6-phosphatase. And then this is going to allow you to get back to the glucose. Not all of your cells, however, are able to do this. So this glucose 6-phosphatase, this is only going to be found in your liver and kidneys. So only your liver and your kidneys are actually able to free up that glucose to leave the cells. So remember the glucose 6-phosphate, the phosphorylation of the glucose was kind of trapping it in the cells. And if we want to let it out of the cells, we're going to need to dephosphorylate it. However, to dephosphorylate it, we're going to need to have this glucose 6-phosphatase enzyme. And this glucose 6-phosphatase enzyme is only going to be present in your liver and your kidneys. Therefore, only your liver and your kidneys are actually going to be able to complete gluconeogenesis. So some of your other cells can say do steps of it, so they might be able to reverse the bottom steps, but they can't take the glucose 6-phosphate to glucose, and therefore they can't ship out glucose for the rest of the body. So they can't go all the way back to glucose. They can only go to, say, glucose 6-phosphate, whereas your liver and your kidneys can go to glucose, and they can ship out the glucose. This is going to allow for specialization of what tissues do what. So your liver, say, is able to both break down the glycogen and let it out, and make glucose and let it out. And there, as opposed to other tissues, which either can't let out the things, or in the case of your kidneys, it can make sugar, it can do gluconeogenesis, but it can't do glycogenolysis, so it can't break down glycogen. And therefore, it's not going to be able to free up sugar from glycogen. And so when we talk about kind of tissue-specific metabolism, it's our liver that's going to be playing the heavy role of regulating sugar levels. Speaking of regulation, next lesson we'll get much more into how we regulate which direction these pathways play through various forms of controlling concentrations and controlling the enzymatic activity. Cool side note is if we think back to when we talked about hemoglobin and how this molecule 2,3-BPG was able to regulate the affinity of hemoglobin for oxygen, and it was able to bind and stabilize the top form, that oxygen not liking form. And so basically it was able to facilitate the release of oxygen. That 2,3-BPG is produced in your red blood cells in an offshoot of glycolysis, where instead of going through that phosphoglycerate kinase step, the 1,3-BPG is actually going to go and be converted into 2,3-bisphosphoglycerate by this molecule bisphosphoglycerate mutase. So that's going to give you your 2,3-BPG, this enzyme bisphosphoglycerate mutase, and that can then be used to regulate the hemoglobin. It can then be converted back into 3-phosphoglycerate by 2,3-bisphosphoglycerate phosphatase in order to keep going in glycolysis. However, you can see that instead of generating ATP, by doing that substrate level phosphorylation, where you're kind of just transferring the phosphate group from 1,3-BPG to ADP, instead here you're going to use a phosphatase to basically just hydrolyze the phosphate group off. You're losing the opportunity to make ATP. However, you are going to be gaining the ability to regulate your hemoglobin. Let's review one more time what's going to be happening in glycolysis and gluconeogenesis. First, we're going to need to trap the glucose inside of the cell so it can't just freely diffuse back out through one of those channels, and so that we keep driving the reaction forward, and so that we're phosphorylating this compound so that we can then trap the littler compounds in the future. In order to do all this, however, we're going to have to invest. So we'll say, yeah, like, okay, we'll spend some money now and we'll get some money later. We actually do want to keep this glucose, not just trap it out. You will want to kind of prevent this stuff from happening if you don't want the cells to take in too much glucose. But if you want the cells to take in glucose, well, now you're going to phosphorylate it. You're going to keep it in the cells. You're going to do this using hexokinase. And the form of hexokinase in your liver is called glucokinase. This glucose 6-phosphate is going to have a lot of different fates. It's going to be able to go places like the pentose phosphate pathway, which is really great if you want to make NADPH, which you can use to like make lipids or combat oxidative stress. You can go and you can take the glucose 6-phosphate and hook it up into glycogen, our storage form of glucose. But for now, we're going to think about going and actually carrying it off through glycolysis. In order to keep carrying it through glycolysis, we're going to need to shift things around so we can phosphorylate the other end as well. When we talk about shifting things around in a molecule, we want an isomerase. Phosphoglucose isomerase is going to allow us to shift the position of our carbonyl so that we free up an alcohol on the end. This is going to give us fructose 6-phosphate, which we can then phosphorylate to give us fructose 1,6-bisphosphate. That fructose 1,6-bisphosphate is now perfectly poised to be cut in two and have two phosphorylated halves that we can interconvert. Actually breaking it in half takes an enzyme called fructose bisphosphate aldolase. Fructose 1,6-bisphosphate aldolase is going to break it in half. Those broken in half pieces, dihydroxyacetone phosphate and glyceraldehyde 3-phosphate, can be interconverted through an enzyme called triose phosphate isomerase. So again, isomerization, we're just kind of shifting things around. We are able to interconvert between these, and now we keep using the G3P, taking it forward in the pathway. That's going to be driving the interconversion of the DHAP into the G3P, driving this pathway forward. Everything in this pathway now is going to be repeated 2 times because we split it in half. So everything that happens from now on, you can think about it happening twice, once for the half that was originally the G3P and once for the half that was the DHAP. The first thing you're going to need to do is now you're going to phosphorylate the other end again. So we have a similar story where we're phosphorylating the other end, but in this case, we're actually adding a phosphate group, not a phosphoryl group. So we're adding a phosphorus with 4 oxygens. So this is going to be an oxidation reaction, and we are therefore going to use NAD+. This is going to generate NADH. And remember that NADH can later be used to generate ATP through the electron transport chain and oxidative phosphorylation. This is oxidative phosphorylation, but it's kind of direct happening as opposed to using the energy from oxidation reactions of the electron transport chain to power phosphorylation. You end up with this molecule, 1,3-bisphosphoglycerate, and this is going to be one of those kind of high energy bonds. Remember, it's not the breaking of the bond that's going to be energetically favorable, but it's kind of the what you get in return. So what you get in return is a lot of energy that you can use to power the production of your ATP. This leaves you with 3-phosphoglycerate. Phosphoglycerate mutase is going to interconvert that into 2-phosphoglycerate. That 2-phosphoglycerate is now perfectly poised for the enolase step. The enolase step is going to dehydrate it. It's going to remove water. The removal of water is then going to set it up so you have this trapped in this sort of enol form. When you release that, now you're going to allow it to go to the keto form. That tautomerization, we call it, is so energetically favorable. It's going to be driving this reaction forward, leading to the production of pyruvate. If we think about going the other direction, what are the steps that are going to need to be different? Well, this step is going to need to be different because it is going to be so thermodynamically favorable in this direction. If we want to go the other direction, that is, if we want to do gluconeogenesis, we're going to need to go an alternative route. And actually, to reverse this last step, we're going to need to take two bypasses. We need this pyruvate carboxylase step, which will give us oxaloacetate, and then the carboxykinase to go back to phosphoenolpyruvate. So we're spending the equivalent of 2 ATP in order to do this. So we have to put in even more energy than we would get from glycolysis in order to do gluconeogenesis. The other two steps are easier to reverse, however. This F16BP step, where we have fructose 1,6-bisphosphatase or F16BPase, is going to hydrolyze that phosphate group, use water to kick off the phosphate group to give us fructose 6-phosphate. Then glucose 6-phosphatase is going to remove the last phosphate group. That's going to take your G6P, change it into glucose, which then can actually get out of the cell, as opposed to being trapped in the cell. So remember, the purpose of that first phosphorylation was largely to trap the glucose in the cell. If you want to let the glucose out of the cell, you're going to need to dephosphorylate it, but only like your liver and your kidneys are going to be able to do this. And so your liver and your kidneys are going to be responsible for getting glucose to the rest of your body.